Okay, good morning. So I think on Piazza, TA already announced your midterm. There are some schedule you can pick up the midterm exam. TA also, I discussed with TA, they will give you some additional time for explanation if you have something unclear. Simply says, you get some points down, you do not know why. You should, discuss with TA. TA may point out what should be the right answer, why you get it wrong. Okay. And after everyone picked up the exam, that implies the next lecture we may have a little time to discuss a little common problems. That means you really have something you cannot understand. We probably can have some explanation in a collective way. Okay. Some students said that they did not do quite well in the exam. So I also should tell everyone should not worry too much because we still have lots of checkup points. Okay. And the final grade will be curved. I originally thought, we may have some, even the maximum, the top tier may get some low scores. Finally, you probably can see the distribution, the high score in the 90s is still quite a good number of people. It simply says we still, even give a reasonably tough exam, we still have a group of students here did quite well, okay, surprisingly well. Of course, you also can see the style is the exam questions is widespread. You just blow up on one tiny problem, you probably will not blow up the whole exam. Okay, that implies you really need to master many things down to the detail. Then you can handle those problems in a short time in a confident way. You can get most of the problems solved nicely. Okay, so the final exam will have the similar style, but simply says you will have a little more time because midterm is always tight. We get 90 minutes. The final exam, you get double of this time. Okay. Then we won't give you, like here, we give you 10-page questions. The final exam, I will not give you like 20-page questions. It's just too much, right? So I probably give you 12-page questions instead of 10. So you have plenty of time to sit down there and work out the questions. Okay. Hopefully you prepare well. The remaining part of the semester you will do well, so you still get a pretty good grade. Okay. At this point, I don't want to give a curve. Some people say, oh, if it's 80 is A or 70 is B or something. I don't want to give it a curve at this point because we cannot decide that. It really depends on in the final time how many people get, on if you accumulate total score, like, 5 to 10% usually give A+. Okay, then we get the remaining one. We give a pretty good chunk of A's. Okay, so you should not worry too much, but you have to work hard. If you don't work hard, you cannot handle those questions. You drop bottom to the class, then that could be a problem. Right? And also, even the bottom, it depends on how big your gap is. Okay, we give you a corresponding grade. That simply says if you drop way, way below the class, then you will really suffer. Okay? But if it's closer, you won't get punished that much. Okay. So that's about the midterm exam. Okay. So then we will start our new chapter. The chapter is on classification. So this is our chapter 8, classification, the basic concepts. We have another one is on advanced ones. Okay, I haven't worked out the final coverage for the advanced ones, but the basic one is very clear. Okay. So this is part of the Athens Acropolis. Okay, it's a few thousand years old. Okay. So we will discuss classification. Actually, if you study machine learning, suppose some student also in the meantime taking machine learning courses, you probably see machine learning we usually call supervised learning, which is classification. Okay? That means you have some training data that experts may give you labels on these training data sets. Okay? Then you take those, you try to work out the model, try to construct, say, decision trees, Bayesian, you can do deep learning, you can do lots of fancy things. Okay? But you can construct a good model. And that model can be used for classification and prediction. So classification is supervised learning. Or you can say it's a major part of the machine learning. Okay. But we have another part of learning called unsupervised learning. Unsupervised essentially is clustering. That means people do not give you the concrete class labels. You need, based on the features, okay, of the data sets, try to work out the different groups. Okay. That different groups we call different clusters. Okay. That's clustering. Actually, in data mining courses, we are going to study both classification and clustering. Okay. So sometimes people call classification model also predictive modeling. Predictive modeling means it can be used for prediction. Okay. However, prediction usually have two kinds. One is predicted the categorical labels, like yes or no, okay, whether positive or negative. Those usually we call classification. But some prediction is try to predict the concrete numerical values. For example, what likely could be the average income, or what likely could be you go down to interview what could be the salary. Okay. So that one actually is on the numerical prediction. Usually people are doing this using regression model. Okay. So that's why most predictive modeling consists of two things. One is class label prediction, most we call classification. Okay. Another one is a numerical value prediction, most time we call regression, okay, because most people are using regression to do such kind of prediction. Okay. But anyway, if you try to model continuous value function, usually we call this one is numerical prediction or regression or some kind of predictive modeling. Okay. But if you want to predict class labels, especially category class labels, okay, then we usually call classification. Okay. And it has lots of applications. You actually go to even the press. Okay. Nowadays, like deep learning is very hot. Then people may ask, what is deep learning? Actually, it's one kind of classification, construct a model. It can be used for like image processing, can be used for information retrieval. Here we list a bunch of them, like a credit card, like approval, like a credit approval, loan approval, whether yes or no. Okay. Whether you got a particular disease, those diagnosis, okay, medical diagnosis is usually the classification process. Fraud detection, whether you get fraud, okay, or even you want to see what kind of web page it is, whether it's a person's homepage or a company's page or something, right? And the classification usually have two stages. Okay, one we call model construction. That means you try to develop a classification model based on the labor data, based on the training. Okay, that means usually people pick up a set of data from your whole pool. Okay, they may ask experts to give labels. For example, if you go to say medical, like a hospital, they want to check whether this tissue is cancerous or is benign. Okay, what they do is they usually have some experts label it. They say, this one, I'm pretty sure this one is cancerous. This one is not. They give you this. You take this based on different features. You try to work out a classification model. You help other people or machine automatically to do this, okay, with good accuracy. That one is a training set. You base on training set. That means labor set. You work out a model. Okay, it could be a decision tree. It could be an Bayesian model. It could be some rules. Okay. So those are model construction. While you construct a model, you are not quite sure your model is good or not. You may need some kind of validation or testing. Okay? That means you may want to estimate how good your model is. That means you may pick up already labeled data, but not in your current training set. Okay? Then you say, well, this one is cancerous or not. If the model gives you the right answer, okay, then you say your accuracy is reasonably high. If it gives you a wrong answer, that simply say you get error. Okay? So then you have to calculate the accuracy. The accuracy means the percentage of the test samples, okay, to correctly classify your object. Okay? So that's a case is accurate. Of course, in contrary to the accuracy, you may have an error rate. I mean, what percentage you will get error, right? And if you use this one to test, that usually we call this part is test set. That means you have training set, you have test set. Training set is used to construct the models. The test set actually is not used to construct a model because you cannot train and test using the same thing, then it's kind of cheating, right? So the test set is independent of the training set. The test set can estimate the accuracy. Okay. But sometimes the test set can be used for validation, or you can call it development. That means you have test set. If you have 5 different models, okay, then you may try this test set to see which model is better. Okay. If you say 5 different models are constructed, I found one model is superior, the other model maybe is very bad. Okay. Then you finally pick up the superior model. That time, actually this test set is used for validation, choosing the best model. Okay. That's a case we actually call this test set is development set or validation set, because it is participating your choice of the models. That means it's part of your classification process. To that extent, we call this test set is development test set or validation test set. You actually use it to choose which model is better. And once this part is done, the real test set is just to estimate the accuracy. You will not intervene with your classification process or choosing the classification models. Okay. So this is about training and testing. Okay. So let's give one simple example. Okay. Suppose you got a bunch of training sets. You want to figure out how the university works. Okay. The university actually have a very important process. It's called tenure process. The tenure process simply says they want to decide whether they want to keep this person as a professor for long term, or they want to say you have 1 year, retention time, you try to find a job elsewhere. We won't keep you anymore. Okay. That means you deny the tenure. Okay. Then you have to think about finding another university or finding other jobs, because the department may evaluate, say, this person is not so qualified to be a professor, right? So then you may wonder, what's the time they get tenure, or you get a professor come, they just arrive. Okay. You want to judge whether this professor already get tenure or not. Those could be important for PhD students because they don't want to follow a professor after 3 years. The professor has to leave. Okay. Then they lost the advisor. They probably have to find another one. That's probably pretty painful, right? Then suppose you may want to figure out how this university works. Okay. What you do is you look at, this is a bunch of names of professor. These are the professor ranks. Okay. These are the years in the university, and these whether you get tenure or not. Okay. So suppose you get a table. Okay. Based on this, you want to figure out what could be the rules for tenure. That means what kind of model construct you can judge whether a new person come or a person unknown. You want to judge whether this person likely already tenured or not tenured before you decide you want to select a professor to follow. Okay. And if you got this training data, you try to work out a classification model. Okay. For example, you watch this. You just say, what kind of professor will already get tenure? Okay. Then you may find if the year is greater than 6, okay, or if the rank is a full professor, okay, even it's new, it's the full professor, likely the chance the professor get tenure is yes. Okay. Why you get this? You can see here, you can clearly see the professor is somehow related to, yes or no is related to number of years. You can see number of years if it's greater than 6, okay, and they got tenure already, okay. But there's one exception. This one only got 2 years, but it's already got tenure. Why? Because this guy come from somewhere else, already got a full professor, okay. Then come here, they give him tenure, but they also, give him a full professor position. So that could be a good rule, right? Then you can judge whether the professor, you already got tenure, you expect he will stay here for a long time, right? So, but how do you work this out? That means how do you automatically, just based on a bunch of data, this is your training data. You can work on a nice model, you can judge whether the professor gets tenure or not. Okay. So that's actually it's a classification process. Okay. And of course, if you got this model, that means you learn these rules, learn this classification model nicely, you already construct a model. Then you actually can get a new data. For example, a new professor came. Suppose this one's Jeff. Is a professor staying here only 4 years, but he's a full professor already. Okay. Then you can easily judge because you got a rule. You said any full professor is already got tenure. Okay, coming here already get tenure. Then this guy only stay here for 4 years. You say, oh, he must already got tenure. So you can easily approach the professor. Right? So that's the use. That's the use of the model because you already know the rules in the university, and you got this professor. You look at the rank, he's full professor. You say, oh, he must got tenure already, right? So that's the usage of the model. That's a simple example. Every student probably a PhD student will encounter this problem, right? Now the problem becomes you got a bunch of training data. How could you work out a good model? What could be a model you can construct? The earliest, probably, the model construction is called decision tree induction. Okay. That one was originally, I think, in 1985 or 86. There was one visiting student, or I'm not sure whether he really got a PhD in Stanford, but he was from Australia, or Ross Quinlan. He went to Stanford, was doing some machine learning. Okay. At that time, there was some kind of model construction, but he did not quite like it. And he knew a little on the information theory or something. He worked out a better method. Okay. And a better method called decision tree. And he even keep doing this. His model called decision tree ID3, and he keep increase this number. Originally, this you can think of induced decision tree or something. That's why I call it ID, okay, inductive thing. Then he used this example saying playing tennis. At what condition a person will go out and play tennis? And now I just change this playing tennis a little into like whether the student will buy a computer. Okay. Suppose if we want to see a person whether to buy a computer, suppose you got this kind of a bunch of table. You got the age, you got income, you get whether it's a student, and whether the credit rating is good. You get this, you say whether you buy a computer or not. Suppose you got this this bunch of data sets. Now you need to make a decision tree. Simply says you want to make a model at what condition, okay, you you can work out the person will buy a computer or what condition you will not buy. Okay. Remember, you got this data sets. The first thing is you can say, anytime later, if I want to check a person buying a computer, I can go back and check the table. What's the problem of it? Anybody can work out if I say, if I get a new person, I want to decide whether you buy a computer or not, I go back to this table because this table is my training set. I got all the data in this table. Like, if you check, this one has, I think it's about 14 rows. That means 14 cases. Okay, I got this. If I got new data, I go back to check this table. What's the problem? Okay. Yeah, maybe very few. Maybe you could not find the guy match any couple, right? Because you can see, you may get a person which is beyond your case, right? You go back, you say, this 14 couple, I get a new person I want to get in, okay? You may not find any match. You have no clue whether this person will buy a computer. Okay? That's the first time. The data is sparse. Training data is sparse. Okay? Another thing is, if you do not work out a nice model, you have no clue at what condition is important. Okay? You have no clue to make a good decision, right? Because you just get a bunch of data. Okay? So to work out a model, essentially is you summarize this data in a smart way. You just say, what is top most important factors? Okay. What are second important factors? You can see, you know the most critical thing, it will be good for you to make a smart decision. For example, okay, you may say there's a telephone number of the customer. Okay. Then later you find telephone is nothing to do with whether people will buy a computer or not. Then you just say this attribute or this property, this feature, has nothing to do with the decision, you drop it. Okay. So you get better insight. Why have to keep telephone numbers inside buying computers? Right? So here you can see, if you can work out decision tree like this, you say, based on this 14 tuples, I actually find the age somehow is important. If the age is middle one, like 31 to 40, I found that they all buy a computer. Okay, that means that if I got a person that is within this age buying a computer, the chance is very high. Okay, but if it's, if it's less than 40, you are going to check whether the person is a student. If the person is a student, you can see the buying computer is very high, but it's not unlikely to buy a computer. Of course, that data says I use it for many years. Nowadays, everybody gets a computer. It may not really match this rule, right? Now, suppose you get ages over 40. Okay, if the credit rating is excellent, actually this person did not buy a computer. Maybe he already got one, right? And if it's fair, you buy a computer. So you can see you got something from this data set. You learn something. Okay? You work out a simple, concise tree, but this tree actually will help you to make a wise decision. Okay? That's why we call this tree is decision tree. The whole thing, you base on this decision tree to make new decisions. That one is you are using this decision tree. But work out this decision tree, derive this decision tree from data. We call this one is decision tree induction. Okay? That means you use data, try to work out this tree. And the problem is, how can I work out tree if I just have this tables? Okay. Now, the decision tree induction method essentially is a top-down recursive construction of the tree in divide and conquer manner. Let's look at how we do it. Okay. So the first thing I can say is, in Ross Quinlan's original paper, okay, he actually worked out a very important thing called entropy and information gain. Okay. Then he used this one to decide how to split the tree, how to pick up the best node or best feature. Okay. So let's look at what he really did. Okay. The first thing is At the very beginning, you can say that all the training data is put on the root. That means for this tree, the root contains everything. Okay? But I haven't generated. Once I generate, I will split the data into different parts. Okay? Then the very important thing is how you work out which one is the top important factor. Okay? I want to put on the very top to split this big root into different parts. Simply say, that's the first thing I want to check before I can make a decision. Okay? That one, to pick up this attribute, become a skill. You pick a wrong attribute, like you pick a telephone number, you'll never get a good tree. You get a very bush tree, it doesn't really give you any insight, right? But if you pick an age, you probably can see, you do get some insight because certain age, they are very clear they're going to buy a computer, right? So age is a good one. How to get which one you should pick? That one, his method is using information gain. Okay. What is information gain? Of course, the formula he worked out. The information gain is based on which attribute carry a lot of useful, smart, decision-related, entropy or information. So how to do that? He actually went back to early days. There was a very important measure for entropy. Okay. This entropy, if anybody studied physics, you probably know the entropy is very important in thermodynamics. Okay. That means if something very, very, the energy is very nice, okay, sharp, okay, usually the entropy is pretty low, but once it becomes heat, okay, becomes just a spread of heat, the entropy actually becomes pretty like random, okay, it becomes somewhat high. Okay, so actually the entropy is something, it's a measure for the uncertainty of, measure whether things is uncertain. So for information theory, you can think it's the distribution is somewhat like this. Okay, if you got a distribution, for example, you have a probability. Okay, if this probability, if you think about the probability distribution, okay, it's more like everything. You can think it's a little for this particular one, it's a little like a Gaussian. Okay, but if you look at the entropy essentially is this probability times this probability takes a log. Okay, so then if you think the entropy, if it's rising, usually it's more random. Okay, so that's why they actually take the -1. Okay, so this is the formula for entropy. That means you have a few points. Okay, if you have m distinct values, okay, and for every distinct value, they have certain probability to be in your model. Okay, so to appear, for example, y1, suppose the probability is 1 is pi. Okay, this means the p1 is the probability to pick up I1. P2 is probability to pick up Y2. Okay, so you have M1, you can say the probability to pick up a particular one. Finally, you get this formula. Okay, and for this formula, you can think about if the entropy is high, that means actually this whole thing, you take a reverse, this one, you have higher uncertainty. Okay, if entropy is low, that means the uncertainty is low. Okay, so essentially you can think about the whole distribution. If this m is 2, you actually can think about things. This h is closer to 1. It's almost like random. Okay. So this is entropy, and they have another one. Is conditional entropy. It's based on certain condition x. Okay. Then what is this entropy you will get? This becomes a conditional entropy. Okay. That is rooted in the information theory. Okay. Then we go back to see how Rosquinland work out using this entropy to work out the information gain. Okay. The general philosophy is this. Okay. He basically took this entropy as the information. Okay. That means that you have a particular thing to put this object into a particular class. Okay. Suppose this in general, okay, this data contains certain information, you can write it in this way. Now you want to put this one into a particular class. Suppose you want to use A, this one attribute A, to split this whole data set into V partitions. Okay, just thinking about it. Suppose you had the age. Remember our decision tree? You may have three things. You may have less than 30 years old, 31 to 40, and greater than 40. Suppose you want to split into this three. That means you want to split your data into V partitions. This time, based on the age, you split into three partitions. Okay. Then, you based on this, you may recalculate after the splitting. You may recalculate their information. How do you recalculate it? You will say, if you want to classify D, that means you want to split this whole data set into these three to see whether your splitting is good or not. Okay. Then you calculate this one. That means after splitting, what is new entropy or new information you will get? Okay. Now you can see, once you split, this D originally is a big D. Now become D sub 1, D sub 2, D sub 3. Okay, then you can see, originally have a big D. Now you split them into three parts, into V parts here. Split into three parts. Each one, they have their own entropy, their own information. Okay. Now you can see your own information here. This is a splitting your portion. It means that if D sub I, this is D sub I's number of tuples. Then you can see, if you split into three parts, you will calculate three partition parts entropy, and you add them together proportion. Okay, that means this is adding together proportion. You get a new information, new entropy. Okay, that means originally you have a big data sets you did not split. Now you say based on the age, I split them into three. Okay, and I recalculate the entropy. If you split it very smart, okay, then your entropy will drop. Your entropy drop means you actually gain some information. That's information gain. Okay, so that means you can see this is the original entropy. This is the split entropy. If this split entropy make your total entropy value dropped, simply it becomes smarter. Like, you know, in the middle of this 31 to 40, everybody buys computer is so clean. Okay, your entropy dropped. Simply says it becomes smarter. Okay, if it becomes smarter, you gain something. So this is the information gain format. It simply says, originally I have the whole thing in the root. Now I don't want it to be in the root. I want to pick up a smart attribute. Based on this attribute value, split them into V parts, into three portions. Okay. Then I recalculate based on this splitting. I recalculate. If the entropy dropped, simply says, I carry more information. You become sharper. Then you get a gain. You have information. Is that clear? Okay. Then what he will do? What you can see, I probably can show here, but I first do a little hand waving. Okay, you think about this decision tree he got. Okay, you actually can put anything on the top to split this tree. Okay. For example, I originally said you can even put telephone number, which is very bad splitting. Okay, then later you'll find you don't get any information. Okay, okay. Suppose at the very beginning, everything is in the root. Now you pick up the first one as H. You split that. You see this split is nice, is smart, because you can see here it's so clean, everything's in the one class. Yes. Okay. Of course, you can pick a student. Whether it's a student, you can put it on the top. Or you can put whether the credit rating is in the top. Or you can put even income in the top. Okay. You can put anything in the top. But some is smarter, simply says you get a better gain. Some is dumb. You do not get gain, you get less gain. Right? So the whole game becomes, if I want to construct a good decision tree, I want to pick up one attribute, like age. I want to put it on top to first split my tree to make sure what I picked get the highest gain. Is that clear? That's his game. This game basically say, I use information gain to calculate anybody how to split this tree. Okay. I have so many attributes. I total have 4 attributes to consider. Actually, in the reality, you have much more. Okay. You may have 20 attributes to consider. But some are very dumb. Okay. We know that, like a social security number or telephone number is very dumb. Okay. So you, based on this, you pick up the smartest one. What is smartest one? The one will lead the highest information gain. You pick that one to split, you get a better tree. Is that clear? That's his game. Okay. He basically say, I just use information gain. I can construct a nicer, smarter tree. What is nicer, smart tree? The tree is small, concise. In the meantime, give you clean decisions. That's a nice tree. That's a decision tree, right? So you, based on this, he first say, take all these attributes to select. And based on the statistic measure. And what he uses is information gain measure. Later, I'm going to show you there are many measures you can use, okay, doing good work. Then there's another thing is, how do you do next step? Okay. The next step is the same. Okay. Once you split this, if everything is in the same class, like everybody said yes, then it's only one decision. Yes, you buy a computer, then you don't have to do anything. Okay. But here you still get a mixed one. You say, if the age is less than 30, you split into a node, but nodes still contain mixed value. Some people buy, some people don't buy. In that case, you still need to do further splitting. That means after splitting this one, you get a bunch of data sets here. Okay. Then you need to make another decision. Another decision means for the remaining attributes, you still have to calculate the information gain to pick up another top rank attribute to split. It happens here. You use a student, you will get a good answer. For example, you can see student is not student, you say do not buy computer. You use a student, they do buy computer. So that's the reason you can see. You can recursively split down the tree. That means you do this in a recursive way. That's why we say examples are partitioned. You can say data are partitioned recursively based on selected attributes. Every time you select attributes, you recursively do, one step, pick up the best attribute, to split it again. Okay. And when you are going to stop, okay. If everything is so clean, they belong to the same class, that means you can make a decision, either yes or no. You have a unanimous vote, then you can stop. Okay. Another one is you may have no remaining attributes to pick. Suppose you say, I have 4 attributes. Then you get constructed tree, you exhaust all the attributes. There's nothing you can further make a decision. Then you have to stop. At this point, who will win? The majority will win. Right? You can see majority of people say buy a computer. You still have a small number say they don't buy. However, you say, okay, the chance to actually buy a computer is so high, I'll just mark this one as yes. Okay. So that's, or you split it, there's no sample left. Of course, in many cases, the stop could be even earlier. You get a majority of people right there, you probably can stop already. If you think, the majority voting is acceptable at this point, you can stop. Now we come down to a concrete example. Okay, we still take that data sets, like this data set. Okay. This actually is originally Ross Quinlan say playing tennis or not. Okay, you're using this kind of table. That's almost the same table. So then we are going to calculate which one we should pick up the top one. Okay. So how to calculate this? Of course, in your homework or you write a program, you are going to do this in a concrete way. Okay. Here we just do this, in the same way as we did it according to this information gain formula. Okay. The formula basically is the first time you need to calculate entropy, or you can say information. How do you calculate this? You calculate this like at the beginning, all the data. Okay. You find that for all the training data, you have 14. You find that 9 were by computer, 5 were not. Okay. If you go back here, you can see there are about 9 where say yes, but the 5 where say no. Okay. Then you say initially, you have this much information. Okay. Then you can calculate their entropy. You may get this number. Okay. So that's the first one. Then you may calculate, what about I use age to split? If I use age to split, your D split into 3 parts. You still remember you have less than 30, 31 to 40, and over 40. You split into 3 parts. While you split into 3 parts, this whole thing, because you base on this age, you also split your training data into 3 parts. Okay, that means less than 30 come here, 31 to 40 in the middle. Okay, then greater than 40 come to the right side. Okay, you split into 3. You got 3 data sets. Every data set you need to recalculate their information gain. Okay, you can see this one. You recalculate information gain. While you recalculate information gain, they have a different proportion. Like the first proportion, less than 30, you have that many people. 31 and 40, you get this many people. Okay, and greater than 40, you get this many people. Right? You get 5, 4, 5. They all divided by the total proportion. Total number is 14. You get 14. So you calculate this, you get a new information. Now you need to look at the information gain. Information gain is the original information minus while you split by age, what's the information you will get. Then that's a gain. Okay, that's the formula. That means after calculation, you find split by age, split right on the attribute age, you'll get this much gain. Okay. Then the remaining is because you have so many choices. You can split by income, you can split by student, you can split by credit rating. You calculate each one, you find their gain. Okay. Then you will check which one is bigger. Okay. Like here, you probably can see, you check these 4, you clearly find that this gain on age is better, it's bigger, right? You can see here. So you will split on age. After splitting this original gain, you cannot use it anymore because data has changed, right? After splitting, your data is split into 3 portions. Each portion you have to recompute their information. Right? And then you calculate again, you can split again. That's the whole game. That clear? Okay. So that's the how information gain being used to derive this decision tree. And this decision tree is smarter than the original data, right? Because it's small, it's concise, it helps you make the right decision. Anything clear or not clear on this? Okay. That's 1985. Ross Quinlan got this formula. And it actually changed that time machine learning. They actually really loved this decision tree, and everybody embraced it. Okay. Actually, Ross Quinlan, a few years ago, in data mining conference, KDD, they gave him an award called KDD Innovation Award. That of course, is the highest honor in the whole research field, data mining. And he was one of the pioneers on this. Now things become a little trickier. Suppose I originally said you have like 31 to 40, greater than 40, or less than 30. You may first ask me, challenging me, say, how do you get the splitting? How you get it? One is greater than 30, another is greater than 40. You pick up this one to split. In reality, people will not give you the split. You got age from very small, like 5 to say 105. You get all these things. And you have to find where to cut. You can find a good splitting point. That means if this attribute A is not like you already partitioned into 31 to 40, it's a continuous value attribute. You still have to handle it. You still have to handle it, right? Then we must determine where to split this one and get a better tree. That's the one that means you try to find the best splitting point of this A. And how do you find the splitting point? Here's the trick. Actually, it's quite straightforward and it's quite simple. Is you first sort A in increasing order. You think about age. You take the smallest one to the highest one and sort them into a sorted value. Then you try to find, because in principle you can split anywhere. For example, you can split based on 15. You say greater than 15, they're going to buy, or less than 15, they're not going to buy. You can take 15 as a cut point, or you can take 35 as a cut point. Where do you find a cut point? In principle, they can find any age as cutting point, right? So the best way is find a midpoint between each pair of adjacent values. For example, in your data sets, you find that the first one is 5, the second one is 12. Then how do you get a middle point? You will say, I do not know where in the middle there, because the new data is not coming yet. You do not even know where is the best one. But you find 5 and 12, what do? You say 5 plus 12 is 17. 17 divided by 2, is 8.5. I take 8.5 as splitting point, right in the middle. I can split this and test whether the splitting is good or not, right? So that means you get a middle point between each pair of adjacent values. Suppose you say, wait, I got one is 23, one is 24. How I do it? Get 23.5, you split it. Every splitting point you need to test which one is best. You can see. You can say the midpoint between each pair of adjacent values is considered as the possible splitting point. That means you take A sub I plus A sub I plus 1 divided by 2. That's a midpoint. That means the potential I cut there may be good. Then you will try to test which one is better. That means if I do not know where to split, I need to test where to split I get best information gain. Suppose we're still using information gain as a test measure. That means you are going to see which splitting point is the best. I'll do my first cut, I split it. And you split into one portion. For example, I say I use 30.5 to split the whole data set. Then you only get one split. In many cases, you may want to even have multiple splits. That means you say from 0 to 30.5 is another data set. I will test where those splitting point is good. I find a second splitting point. Maybe 30.5 to 105. I may find another splitting point. I have to test where is the best splitting point. That means based on your training data, you try to find where splitting point, you can split them into a reasonable number of partitions. That's how to handle this continuous value. Is that clear? Okay. Yeah, the question is how many times you have to split. Usually, you get a reasonable number. Usually, most people say 2 to 8. It's a good number. But that's still quite a big choice, quite a number of choices. Because split 2 is a minimum. You have to split by 2, otherwise it doesn't work, right? But you split 2 fragmented, it probably doesn't really make that much difference. So that's why you read some papers, it just is 2 to the 8, it's very loose, right? So it really depends on the application, and also depends on information gain, how much you will get. If you don't get much gain, you probably don't split it, right? Okay. So that's the splitting on the continuous value. Okay. Then, besides this information gain, okay, Ross Quinlan keeps working on what is good one to pick up. You know, his initial one is just the information gain. But later he found the information gain has a little problem. Okay. The problem is usually you got a large number of splits. That means if you split suppose the age into 10 different portions, maybe your information gain is, total information gain is quite big. Okay. But it's not a very nice use split things into 2 small ones. Okay. The same thing as if you use other numbers, the number has lots of values. For example, if you say the status income, you partition them into very fine one. You may also get a good gain, but it's also not a very nice trick. Okay. So then he says he wants to work out a ratio which can compensate that, not too much bias on a very large number of values for any particular attribute. I mean, you want to be fair. Then he worked out one called split info. It's another ratio. Okay, that means he tried to normalize it. He used this one called gain ratio instead of information gain. The gain ratio basically is use information gain divided by split ratio, split info. Okay, split info essentially is kind of an adjustment. Okay, that means if you look at this, that means originally you get information gain. Now he basically say, if you get too many, I have to punish you a little. I reduce your gain a little. How to reduce gain? He uses this formula. This formula simply says, if you split into 2 fragmented numbers, your V is quite big, and this number actually tends to be bigger. Bigger you divide this, the gain actually will be reduced. Okay. So he basically tried to use this formula just to compensate. Okay. For example, you take an income. If you took income, suppose you got this, you can calculate the gain, the split info is 1.557. That implies you have to divide something more than 1. Okay. So that means your income divided by more than 1, maybe your age divided by even bigger. Okay, then the age will be, reduced a little, but you still can compete with them. Compete not based on the information gain, but based on gain ratio. He revises one a little, okay, to be a little fair. And based on this, he decided the splitting point. He worked out a software called C4.5. C means a classifier. Okay, 4.5 is his version. Okay, his version number, because he keeps working on this decision tree, and he worked out one most popularly used is his C4.5, which actually he get a book. If you go down there, the book contains all the source code of his C4.5. He published. Okay, that means you buy the book, you almost buy the software. Of course, you can code it in. Maybe C4.5 open source, you go to the web, you can find it. But he's smart. He actually worked out an even better version called C5. And he never published the C5 code. Okay, and that means you want to get a C5, you have to buy his software. Okay, otherwise you use his a little less competitive version, C4.5, which is open source. Okay, but anyway, you are welcome to buy his book or get his code. And it's a very popular use of decision trees. Okay. So that's about a gain ratio. But that's not the whole story, because after he got this information gain, people actually invented many statistic measures. They say, oh, using your information gain can get something. I can use another one. Okay. Actually, there are many. One popularly used one called Gini index. Okay. That one was used, I just give you two examples. One was used in the software called CART. Okay. That's one statistician actually used this one quite a lot. IBM later worked out a data mining software called Intelligent Miner. They use this Gini index as well. The Gini index computation formula is a little simpler comparing to information gain. During information gain, you see you have a probability. You take a log, say P times log P, and then you sum them up. Okay. You take a log. The computation is a little more involved. Of course, you can say log is nothing, right? Here, this one is even simpler. The simpler means this is probability. You just say, you can square them, add them together, and this Gini index is 1 minus the same. Okay, so the computation is very less involved. Okay, then that P is the probability, or say relative frequency of class J in the whole data set. Okay, so then you can, based on this, calculate Gini index. Okay. Then you can calculate a Gini index in the similar way as information gain. You look at the formula. The formula actually is very much like information gain. You can see this is your Gini index. This is splitting according to attribute A. A split data into several portions. Okay. Suppose split into 2 portions. You can calculate this way. Okay. Actually, Gini index, the first split, they always split into 2. That's why I don't write down everything. Okay. You split 2, then you can split 2 again. You can every time you do binary splitting. Then you actually can calculate this gain, but they don't call this one as information gain. They call reduction in impurity. Okay. Remember, impurity is similar to the entropy idea. Okay. That means you want something to be pure. Pure means if this one, everybody buy a computer, very pure, or everyone do not buy a computer, it's also very pure. Once things mixed up, it's not so pure. Right? So reduction in impurity simply says, if I split according to attribute A, my impurity is somehow reduced. That means if something becomes more pure, then it's better. That's why you can see this is the Gini index. This is the Gini index after splitting by A on the attribute A. Then this one essentially is a reduction in impurity. Or you can think this kind of information gain calculated in the term of Gini index. Okay. So then you can use this one to find the smallest gain or largest reduction in impurity. Then you can choose as a splitting node. Okay. So that's almost the same game, just a little different calculation, different format. Right? So that's another way to construct a decision tree. Okay. So if we use the same formula, the same data sets, we use Gini index to calculate, you probably can see you can calculate the same thing. You can see this is the whole data sets. You have 9 people buying computer, 5 do not buy. You get this original Gini index. Okay. Then you can, based on this, you can calculate if you use information income, low or medium or high, use this one to calculate it. Okay. Or you can see, you can split. Remember, everything in Gini index is binary splitting. That's why at the very beginning, you can split in this way, or you can split in the other way. So you can say one way is I group high as one node, one group, low and medium as another group. I want to split in this way. You can calculate the Gini index, what is the better one. Then you, based on this, you decide which one to split. So this one, because every time you do the binary splitting, this one you can easily use for continuous value, because you try to find, among those continuous values, you try to find different kinds of grouping, and you decide where to split. Okay. So that's another measure we call gain index for decision tree induction. Actually, there are many ratios, many measures. We discussed about information gain, this about gain ratio, this about gain index. You actually can see people analyze to say which one is better. Okay. They found that information gain has some bias towards multi-valued attributes. That means you have many, many different scatter values. The information gain tends to be higher. Okay, it's a bias to this. And the gain ratio try to avoid this problem, but they actually tends to prefer unbalanced splits. That means if one is much smaller, one is much bigger, then you split, actually this gain ratio becomes better. Because usually you get a very small part tend to be quite pure, and the bigger part is more mixed. Actually, they, based on their gain ratio, they actually give you a better gain ratio. That's also a little problem, right? And the gain index is biased on multi-valued attributes. That means you get a multiple value, you also can get this. But if the number of classes is very large, you know, if the number of classes is very large, because every time you do binary splitting, they make the tree quite deep. Okay, that's also the problem. Okay. But they tend to favor the test result in equal size partitions and purity in both partitions. That means they tend to say among the equal split, actually get the best one. Okay. Sometimes it may not be the best that you can be. But you can see these two are a little extreme. This one says unbalanced one is better. Okay. But again, this is more balanced one is better. So it depends on your usage, right? But there are many. Okay. I just list a bunch of them. You probably can see. If you want to get decision tree, you can use several others. One called Chai. Chai actually is using the chi-square test. Okay. Some people call it chi-square or whatever. They use this one called Chai. You can see this is inductive decision tree, right? Basically based on this. There's one called C-SAP. That's another static measure. Another one using G-static is using some kind of approximation of chi-square distribution. There's one quite popular used called minimal description length, MDL, minimal description length principle. That one basically say, actually, if you think about decision trees, also kind of try to make your decision length is quite small. Okay. The minimum description length principle means this: you can construct many trees, you can construct different things, but if finally you make a good decision, if your tree length, the total length of your model, that means total size of a model, you can say the number of bits. Whatever, the size is small, means if the total size is small in your model, that's a better model. Okay. So they basically, based on this, they work out called minimum description length. It means no matter what method you use, no matter which tree you constructed, I finally test which one is the most compact. The compact one will win. Okay. This one has a long tradition. Okay. There are lots of fans on this minimum description length. Okay. The typical route, they go back to, like, I think it's, we got in Polish, early days, there was two theory. Originally, the people say you got, Earth as the center of the universe. Everything is surrounding the Earth, okay? And the sun is surrounding the Earth, and the planets, they're surrounding the Earth. But the planet, because the planet, if you take the sun as the center, the planet, the whole trace, the route, how they move, it become very simple because it's just a quadratic equation. It's like a circle or ellipse, right? But if you take Earth as a center, the model is very complicated because you think about how do you predict how the Mars is moving or how the Pluto or Jupiter, we say, how they move. It becomes very complicated. Okay. So Copernicus, who was the Polish famous astronomer, he first proposed the sun as a center, okay, for Haller's something theory. Okay. The other one take the geo, like the Earth as a center, and he basically showed. That time there were no satellites. There was nothing, right? But he just based on the telescope observation. He says if I took the sun as a center, the equation workout is extremely simple. It's just a quadratic equation. Okay? And I can predict everything. If you take Earth as a center, the equation will become much more complicated. The simpler one is the winner. Okay? So basically, I have the minimum descriptive length to describe how the celestial body is moving. Okay, so the scientists, even without checking which one is really right, because how do you judge? You only have telescope, right? So most scientists immediately embrace this Copernicus theory because they assume the movement should be somewhat simpler. Of course, later people discovered the gravity theory, Newton's gravity theory. They can't explain it. Okay. Otherwise, you just take the minimum descriptive length. That likely will be the truth, the better one. So that's the same thing when you work out decision tree. You take the minimum whole tree, the minimum descriptive length, you achieve the same result. This tree is a better tree. So that's the minimum descriptive length. And there are things on multiple splits. That means you base on a multiple variable instead of a single variable. Remember the decision tree we work out for Ross-Quinn length is just single variable to split. But sometimes you use 2 or 3 variables combined to split. Maybe you get a better tree. Okay. So that's the one, like a card may use multiple variables. Means I use more than one variable as a decisive factor to split the tree. Okay. And so which one is better? So until now, most people say even a very simple one, like Ross-Quinlan decision tree, actually will work reasonably well. Okay. Minimum distribution length is very popular. Many others are also quite somewhat used. Okay, in practice. For example, like a card in industry, actually used also very popular in like a medical science or something like this. But overall, people say most of this will give pretty good results, but none of them is significantly better than the others. So that's why you get multiple different measures to still use. And of course, you will see there are many other later I will give you, for example, like deep learning or something now is so very fashionable. But the tree has one advantage, is much more explanatory. That means you go down to medical science, you say, I give you a model, say this one is cancerous, this one not. The medical science, the first question is why? Why you claim this? You have to explain to me. Okay. If you got something hidden, support vector machine and neural network, you say, I cannot explain, it's so complicated. But you just trust me. Okay. Actually, many doctors, they don't trust me because none of them is 100% true. Anybody knows. But you cannot explain. I have a lot of experience. I can explain it. That's why a lot of people still like tree because they say it's easier to explain. I can watch it. I can believe this is an important factor. This is second important factor. I know it. So your tree constructed match my experience. So they will believe the tree. So even until now, the tree is simpler, but still lots of people are using it, right, because it's easier to explain. Okay. So even in this KDD 2016, there was one almost win the best paper, but his presentation was like a best presentation award, got a $1,000 or $2,000 cash, okay, just by the nice presentation. Actually, that was one professor in University of Washington. What he worked out is just to make any model more explanatory. It means easier to explain why. Okay. And he actually shows he has a way, no matter what kind of model you generate, I can easily convert them into some kind of like a tree in this kind of form. Okay. It's very easy to explain why to all the practitioners. And it, the paper is really nice, and the people really like it. So then the tree, if you see that, there's one thing is you can keep, if you have many attributes. Suppose you have 20. Each attribute, you take it, you split the tree. If you get lots of training data, you can split the tree quite deep. And as deep as you use all the variables. You have 20 features, you use all the features, you get a tree 20 layers deep. Then the problem people may ask you, is this a good thing you get so deep tree, or is it a bad thing? Okay. Most people will say, no, it's a very bad thing. Why is it a very bad thing? Okay. The first thing is you may get an overfitting problem. What is overfitting? It means you get a tree so deep, finally you get this tree at a certain layer. You only have 2 or 3 data to support it. Okay, suppose you originally have 100 data sets. You start splitting. Why are you splitting down? You think about it, you're splitting, even you get an even split. You think 100 is split to 50. You logarithmically, you will not go very deep, right? Plus, most of the split is not even. Finally, you have only 1 or 2 data sets to support this case. That's very dangerous because, you think about it, you split so deep, okay, you have almost no support. You get only 1 or 2 cases support you. Unlikely you get a new case exactly match the case you get exactly. It simply says, you are so unconfident based on 1 or 2 things you make a decision. You need sufficient data to make a decision. That tree you get so bushy, so deep tree, this tree may overfit your training data. It means they tailor to your 1 or 2 training data set. This 1 or 2 object decide this branch of tree, and you get a new data, you put it in, unlikely your classification will be accurate. You support too small. You're just thinking about it, if in the election you split into so small number. For example, suppose you have 1,000 samples who you are going to vote. But once you start splitting, some part again majority data, you still have like 20, 50 cases supported. Finally, you get this case is only 1 or 2 people are supported. Then unlikely you get a new people coming in. They will vote in the same way as this 1 or 2, right? So that's the reason you get a poor accuracy. On unseen samples, on the new data coming in, you will make mistakes. So that's not a good trick. Okay. Then what do? You say the tree you did is just overly dark. It's too deep, too bushy. It's not good. The best way is to cut it. Okay, you say you get so deep tree it doesn't really work. Okay, because the tree got very little support. Best way is to say you get only small number support you. I won't believe you. I cut you apart. I don't split anymore. So that one called post pruning. That means you fully grow this tree, and finally find the tree actually is not good because while you go down towards the leaf, you get a very small number support you, cut it. Okay. So how to cut it is you can say, I take the new data sets coming in. I think you make a mistake. You can see that you make a wrong decision. So this branch, you made a wrong decision. Anytime you made it wrong, you cut it. I make the tree less deep, but a better quality. That one called post-pruning. Okay. Another way is we call pre-pruning. Pre-pruning means even I do not go that deep to construct a tree, I stop somewhere. Okay. Why? Because you don't have good samples, you don't have a lot of samples to test it. I stop here, even it's not so pure. That's pre-pruning. Okay. So next lecture, we are going to continue this decision tree, and then we get into other methods. Okay, thank you.